In the main room, you guys back? Maybe they're not back yet.
Oh, there's definitely. Can you give it another minute or two?
Yeah, there's a couple people missing. I'll just watch the room video.
Jerome, are you at the fields right now? I know you're doing your online talk, but you said that you were gonna be there eventually, right?
Yeah, I was there last week. Right now I'm in Montreal because I have family here, and I'll be splitting also my time with Waterloo. So, but I will be at fields, not all the time, but I already have an office.
Cool. Good to know. Yeah, I'm looking forward to officially meeting you and okay, so I guess we should start now.
Do the people in the room hear us?
Yeah, do the room 230 people? Maybe not, since they
Yeah, seem to just be walking around and not hearing us.
Must have turned off those speakers.
Let me, I guess I'm gonna put something in the chat.
Anya,
Let's
you can hear
see.
everybody. I know you can. I was just in there.
Oh, okay.
You can hear everybody. They're just ignoring us. I see.
So we were just
Oh
about to
wait,
say,
Robert's about to sit down. I think once he sits down, everyone will pay attention.
we were just about to say nasty things about the people in the room, so I'm glad that Brian made it.
Okay, I will just switch to my view of Beam and Ehrlich there.
Yeah, blame it on Ben.
Weights also on top of this.
Okay, so can people in room 230 hear us? Yeah. Yeah.
Yes.
Okay.
Yes.
Okay, great. Okay, so then let's get started with our second talk. So Jerome will speak to us on stability of singularity resolving effective theories of gravity. Okay, please, Jerome. Thank you.
So first of all, can you hear me well?
Yes.
Yep, he's online.
Yes.
And can you see my cursor if I move it around the screen?
Yes.
Yes.
All right, very good. Let me start. Yeah, so the title, Stability of Singularity Resolving Effective Theories of Gravity, is maybe a bit technical, but let me start by saying that my goal today is mostly to present the motivation and really an introduction to the kind of questions we're trying to ask in this particular area of research in physics. But in light of the thematic semester and really in the spirit of bridging mathematics and physics, I'll really try to avoid unnecessary physics jargon. If I do, please stop me, ask me questions if something's unclear. I really hope this can just stimulate the discussions. And yeah, I will not present too much details, so I hope you will get something out of this and yeah, give you just a sense of the kind of things we're trying to do in this area of physics. So let me start with some motivation. I will start with the general ideas of the singularity theorems and general relativity that were found by Roger Penrose and Stephen Hawking. Let me give you, as an example, the formulation of Penrose theorem of 1965. They all have different assumptions, but the general structure is more or less the same. There are some assumptions that have to come in. For instance, in this realization, one has to assume the null convergence condition, sometimes abbreviated NCC, which says that in physics notation with indices, the contraction of Ricci tensor with a null vector twice has to be greater or equal to 0 for any null vector. So null means that the contraction of the vector with itself is null. In, I guess, more mathematical notation and abstract notation, we would say that Ricci contracted with a null vector twice has to be greater or equal to 0. To understand more physically what this condition says, if we assume general relativity, if we assume the Einstein field equations hold, here again in indices or in abstract notation, where on the left-hand side we have the Einstein tensor, which is the Ricci tensor minus a half, the metric tensor times the Ricci scalar, the trace of the Ricci tensor, is equal to, on the right-hand side, the matter content, the energy momentum tensor, times a coupling constant, A times pi times the gravitational constant, G Newton. The speed of light also enters here, but we usually just set it to 1. And if those equations hold, then the null convergence condition is simply equivalent to null energy condition, which states that the contraction of the energy momentum tensor with a null vector twice is greater or equal to 0 for any null vector again. So this is the assumptions that come in with regard to what is either the geometrical input in the space-time or the physics that you have in the space-time. And there's a few more assumptions that have more to do with the general structure of the space-time. In particular, one has to assume that there exists a non-compact connected Cauchy surface in the space-time manifold, and that there exists a closed trap surface in M. And if you meet all these assumptions, then the conclusion is that the space-time manifold cannot be null geodesically complete. To have a bit of an intuition for what is happening there, let us look at a set of null geodesics that are not intersecting. So we'll call this null geodesic congruence. And you can describe the geometry of these null geodesics.
Sorry, can I ask a couple of questions about the first slide?
Of course.
So, what does it? Are you going to tell us what a closed trap surface is?
Let me try to give a short answer. Physically, the way I understand it is that you have a surface within which things are starting to fall towards each other. That is a very physics answer. There is a precise mathematical definition which I cannot give off the top of my head. But in the next slide here, I will connect where this is sort of entering. Yeah, if you look at,
is this? I mean, can I understand this as a sort of mean convexity condition on this? So first of all, is this surface a three-dimensional surface or a two-dimensional surface in a three-dimensional slice?
I didn't hear very well. Can you repeat?
Sorry, when we talk about closed trap surfaces, are we talking about a two-dimensional subset of the Cauchy surface, or are we talking about a three-dimensional time-space surface, hypersurface, whatever?
Right. If I recall correctly, I think it is a two-dimensional subsurface of the Cauchy hypersurface.
Perfect. Okay.
Yeah.
And my guess is that maybe closed trap means that is that a local condition? Is it just telling you that the area is getting down no matter how you push the surface into the future, or is it a more global condition than that?
No, I think what you said about locally makes sense.
Okay. Thank you.
Okay, so here, if we are looking at null geodesics, we can describe the geometry of those with respect to an expansion scalar, theta, which is the divergence of the null vector, written in various ways here, whichever is more enlightening to you. A shear tensor, or if you contract it with itself, then it's a scalar quantity, which tells us about a deformation of this geometry of null geodesics. And there's an affine parameter that tells you sort of the length along the geodesics. And here we're assuming there's no vorticity, sort of no rotation. So this hypersurface, we say that it's hypersurface orthogonal. And the equation that it's going to respect is the ratio Dury's equation, and it's the following ordinary differential equation. And then here enters the contraction of the Ricci tensor with a null vector twice. And if the null convergence condition holds, this is always positive. The sigma squared is also always positive definite. Therefore, this ODE becomes a differential inequality, and you can solve it, and you get this inequality as a result. And if initially you're in a set where, in a region of space where this expansion scalar is actually contracting, so I think this is where it connects with this intuition of trapped surface here. Then you can show that in finite affine length, so within this upper bound on lambda, you're going to have a divergent expansion scalar or contraction scalar in that case. And there's a question?
No, I was just going to say, I could, I'm sure Robert's already noticed, but the theta here is the Lorentzian analog of mean curvature, as Robert brought out, and it would be negative for a closed trap surface, so it's concavity condition.
Yeah, that sounds correct to me. So yeah, so physically what this is saying is that within a finite distance or finite time, if you will, the geodesics would come together and cross each other in what is known as a caustic. And this is a sign of these geodesics being incomplete, or the congruence being incomplete. At this point, this is not saying anything about the global spacetime, and the singularity theorems are really global theorems, but this is, I hope, just giving a bit of intuition for where something like a null convergent condition enters into having some notion of geodesic incompleteness and potentially singularities.
Could I also interrupt to make a slight and very pedantic, perhaps pseudo correction to that? So as the geodesic carries along, as the geodesic moves forward, it really let's consider it as transporting along little area element of surface. And that area element collapses at a caustic, but it's not quite the same as saying the geodesics cross. They don't actually have to intersect. It's just that the dimension of the the dimension of the area element that they're carrying along collapses, basically, which may or may not indicate crossing.
Is this like the difference between a cut point and a conjugate point, Eric?
Yes, that's exactly the difference. Cut point is more general. They will either cross or the exponential map will degenerate, whereas caustic, it's the exponential map is becoming singular. They're not necessarily crossing.
So then I have a question, because in Riemannian geometry, we do not call it a singularity just because geodesics meet. So cut and conjugate points are not causing any singularities. Is there something different happening because these are null?
There isn't anything different happening, but when you eventually get to the conclusion of geodesic incompleteness, and so the argument, as you know, in the singularity theorems, generates a contradiction between there being a conjugate point and, for another reason, there can be no conjugate or cut point. And so when you have that contradiction, the only way out of it then, of course, is that you can't get to the cut point. There must have been a singularity in the sense of geodesic incompleteness. But of course, that's different in Riemannian geometry because you have Hop-Renoff, so then many different kinds of singularity are equivalent, but here you don't.
Right. Okay, thank you.
Sure. Sorry for taking over, Jerome. My apologies.
This
Not
is
at all.
Eric Wolgar, for those who don't know.
Oh, thanks. Yes.
No, well, in 2 slides I already achieved what I was hoping, that we have these discussions and that I can teach you something, but I'm learning already, so that's good. And so let me move on. What I will say is that in general, if we have a geodesically incomplete spacetime,
Okay, perfect.
it does not necessarily imply that the spacetime has a singularity. Then there's this notion of extendability, whether a geodesically incomplete spacetime can be extended into something that is non-singular, or whether it is inextendable, and then whether there really is a physical singularity in that spacetime. I won't get into the details about this. Perhaps this could be for another talk, and especially in the context of cosmology, where I studied this a little bit. But let me just say that some examples of spacetimes that appear complete, but which can be extended, would be, say, flat de Sitter space. But alternatively, examples where really the spacetime is truly inextendable, so singular, and in particular where we have physical singularities, such as scalar curvature singularities, would be like at the center of black holes or at the Big Bang. So let's look at what happens when there really is a scalar curvature singularity. As I said, examples would be at the center of black holes or at the Big Bang.
Sorry, you mentioned on the previous slide these curvature singularities which are non-scalar. So that means somehow that that like the tidal forces are diverging, but they're canceling out in such a way that the scalar stays bounded?
Yeah.
Like the stretching and the compression balance each other out, but they both diverge?
Yeah.
Okay, thanks.
Yeah. Right. But the more, the more standard types of singularities that we're used to seeing are the scalar ones. And examples of scalars that could diverge could be like here, the Kretschmann scalar. So schematically, the Riemann squared, the contraction of the Riemann tensor with itself. And
sorry, can I also interrupt since everybody is asking? Could you go back to the previous slide again? Wait, are you saying that the flat de Sitter space is extendable? Because in Riemannian geometry, complete things are not extendable. I'm kind of, I guess my intuition is failing me.
So what is happening in de Sitter space, if you work in flat de Sitter space, you find that null geodesics are incomplete. And this is happening at what we would say the time is going to minus infinity. But really, at this point,
sorry, you're looking at incomplete case. Okay.
All that I'll say is that this point is not a singularity. It's really an artifact of the coordinates you're using to describe flat de Sitter space. And you can see in different coordinates that describe de Sitter space that actually the full space-time is non-singular. And usually, you have different branches that are connected at that point. The contracting de Sitter space.
Right, but complete space-times are not extendable, right? At least I know in Riemannian geometry they aren't. I'm not sure if it's true here too.
Yeah, so maybe this is a question of terminology. I guess what I would say is that then when you have global de Sitter, then this is a complete space-time. I could be corrected here, and then surely you cannot extend this anymore. You already have.
Right. That's what I was thinking. Right.
Yeah, exactly. Whereas if you just have flat de Sitter space, this is not the whole space-time. That is the point.
Okay.
Okay, so here I was saying that when you approach these singularities, these scalar curvature singularities, you're really quite clearly in a strong curvature regime. And what I want to emphasize now is that in such a regime, general relativity as a semi-classical theory might very well break down. And the way we say this in physics is that actually general relativity is a non-renormalizable theory as seen as a quantum field theory. Now, I will try to give you a bit of intuition for how this is coming about. So let us consider gravitons that are propagating and interacting, we say scattering, on a Minkowski background. So we imagine expanding our space-time metric as being Minkowski to 0th order, so flat, empty space-time. And then on top of this, we add small fluctuations, small tensorial fluctuations, h, that come with a coupling the square root of Gn. Then we look at the action for general relativity, which is a very important tool that we have in physics. So what this action is the integral over the whole spacetime manifold of d4x square root of minus the determinant of the metric. So this is what physics notation, perhaps it's more enlightening for math people that this is like the volume element or the Hodge dual of unity, or by d4x, this is really like the wedge product of the basis 1 forms. But I'll stick to this notation. And then the integrand is the Ricci scalar divided by 16 pi times g Newton. And when you expand this about Minkowski with small fluctuations, what you get is a perturbative series where to leading order you have this what is known as a kinetic term, and then you start having interacting terms here with, you have 2 instances of this h, now 3, so this is like a cubic interaction term, you would have a quartic term, and so on. So this is very schematical, but just to give you the flavor of this. And then we can use such an action to compute amplitudes, so transition amplitudes, meaning say computing what is the probability of having 2 gravitons coming together, interacting and coming out. So 2 gravitons coming out. So we usually depict this in such graphs known as Feynman diagrams. And as I said, this is really a perturbative expansion. So the way we compute this is to first look at the simplest types of graphs you can draw. So at first you would have cubic interactions here happening at this vertex here and at this one right there. And you have different ways these can cross each other. So this is what crosses mean here. And each of these vertices contribute a factor of square root of g Newton, the coupling entering in this cubic interaction term. Then you would have a quartic type vertex with a factor of g Newton. And then you can start having loops. So here you have loops with cubic interactions, here a loop with quartic interactions, and so on. And really the full amplitude, the full transition amplitude, to compute the full probability, you would have to sum all possible diagrams. And so really this is an expansion in the coupling constant, square root of Gn, divided by lambda, lambda being the wavelength of the graviton fluctuations. So the wavelength, or if you will, the energy of these fluctuations coming in and coming out tells you about the relative size of these interactions. And each of these graphs are going to contribute a factor Gn over lambda squared to the power 1 plus the number of loops you have in this diagram. Because the more you have loops, the more you're going to have vertices, and at each of them you have to have a certain power of the coupling that tells you about the strength of the interaction. And the full amplitude, this is what this means here, the amplitude of the process h to h going to h to h is the sum over all these diagrams, including all the loops of this factor. And clearly, if you have a very large wavelength, so large wavelength is equivalent to having small energies, or small wave numbers, then this can converge and you're going to have a finite number. But if you have a very small wavelength, so very high energy gravitons, then you can see as you you try to do this sum, it's going to diverge, and the perturbative expansion is really going to break down. And in physics, we say that this is a sign of strong coupling, because all of these interactions here have a very large strength, and you cannot sum them up. And really, general relativity, seen this way as a quantum field theory, cannot apply. It's really breaking down in that regime. And another way of putting it is to see that to get a sensible number, you would have to remove these divergences, and you would need an infinite series of what we call counter terms. So you'd have to subtract the infinities by including new terms in your action. And again, schematically, you would have to include in your action a sum over all possible scalar contractions of the Riemann tensor and covariant derivatives thereof with various coefficients, precisely such that you remove all of these divergences and get a sensible finite number. All I want to say here is that really this is motivating us to go beyond simple general relativity if you're going in a strong coupling regime or in a strong curvature regime. And it's certainly true when you're trying to study physics near singularities. Now, a few more words about the null energy or the null convergence condition, or equivalently the null energy condition. Again, if we look at this from the point of view of quantum mechanics, quantum physics, there are well-known examples, well-studied and well-accepted in the community, of matter that can certainly violate the null energy condition, at least locally. So what this is saying is that if you compute the contraction of the energy momentum tensor with a null vector twice, and you compute the quantum expectation value of this quantity, then locally you can find instances where this is negative. So you can think of this as being sort of negative energy density. And the Casimir effect is a well-known example of such a situation. In quantum gravity, there might still be a notion of null energy condition, but perhaps something more like an average notion of the null energy condition. For instance, there's something called the ANEC, which states that if you integrate the null energy, the quantum expectation value of the null energy over a whole achronal null geodesic, then this is the quantity that's going to be positive, greater or equal to 0. And this has been proved in various contexts for various physical settings. And so a conjecture is that this would hold in full quantum gravity. There are other proposals that are somewhat more local as well, such as the smeared null energy condition, where the idea is to, in addition to computing the quantum expectation value of the null energy, we also want to average over some time scale, or the terminology is to say that we smear over some time scale, and it introduces some smearing function g of lambda, which is square integrable. And then this smeared negative energy can be actually negative over some time scale given by this tau, which you get by computing this integral. And how much it can become negative is given by an order 1 number, which is not known from fundamental physics, and then divided by the gravitational constant. My point here, without going into the details of these proposals, is to once again really stress that the assumptions that are entering in the singularity theorems might very well break down. And then it bears the questions whether singularities are avoidable in quantum gravity, or whether it could even be that they are forbidden. And the reason I'm writing down these questions here is that in quantum gravity, we have various proposals such as string theory, loop quantum gravity, and so on. And without discussing any one of them in detail, I'll say that they all suggest some notion of a fundamental minimal length scale, or equivalently rather, some notion of maximal curvature scale. And if that's true, then we it certainly motivates us to revisit the question of space-time singularities and what happens to the physics in those regimes. A problem is that studying quantum gravity is very hard. Let me just say here that perhaps we need new mathematical tools, and something like low regularity geometry could be helpful. Today, what I'll show you, what I'll try to do instead, is to come up with an effective theory of gravity. So what this means is basically we're going to try to see how we can modify general relativity in a way that could characterize the low curvature regime of quantum gravity. So we want something that is going to recover general relativity in a very low curvature regime, but which is going to start behaving a bit differently when we approach singularities, and see then what is the phenomenology of the theory. And then the hope is that we can test such theories, see if they yield any sensible solutions, see if they're stable, see if they have any predictions that we could then go ahead and observe or measure. So one approach that, before that, let me just say that, yeah, I will present one approach, but let me just say that there are actually many approaches to modify gravity, and they are motivated by various physical considerations. So the motivation I presented today really was in the context of singularities and strong curvature regimes. But even in low curvature regimes, we have indications that general relativity might not necessarily break down, but might be different, might be modified in some way. Dark energy is maybe the most well-known example of that. We do not have a good understanding for why today's universe seems to be growing at an accelerating rate. And so, as Ghazal mentioned, the most conservative solution to this is that there is a cosmological constant, and it's just there, and it has a certain very small value, but we don't understand why. But it could also be that it's a manifestation of gravity being a little different than just plain general relativity. Also, dark matter could as well be a theory of modified gravity. Just a moment. Yeah, so for dark matter, we usually, the simplest theories say that it's some new particle that weakly interacts with light, with the standard model particles. But there are proposals that suggest that it could also be a manifestation of a modification to general relativity. There are pros and cons with this, but let me just say that it is out there, and it's something that's being studied. Now, come back to today's motivation. We are going to try to look at modifications to general relativity that have some notion of maximal curvature. And in fact, we can construct classes of such theory that have intrinsically a notion of maximal curvature. We usually dub those limiting curvature theories. And this is something I studied a little bit. So again, where this fits in the landscape of modified theories of gravity could be a subject for another talk, perhaps. But for today, I'm going to focus with just one realization of this concept. And it's a theory known as the Cuscuton. So this was proposed some years ago in particular by Nyayesh Afshordi and Ghazal Kashnishiani, both now at Perimeter and the University of Waterloo. And so the proposal goes as follows. The action is, first of all, that of general relativity. But to this, we add a scalar field. So also, as Ghazal presented, adding a scalar field is something that is quite common in cosmology, and especially in the context of primordial cosmology, of inflation. But it is, let me say that it's more general than this. But here for the Cuscuton, the scalar field is a bit peculiar. It's somewhat non-standard. So it has a potential energy, V of phi, And then this term here, which would normally be like the kinetic term, this is where the theory is very different. So inside the square root here, x is a quantity that would normally be the kinetic energy, so the contraction of the gradient of the field with itself. But instead of being just x, it enters in the action with a square root here. And this will have various implications, as we'll see. The equations of motion that follow from this action, we can get from varying the action, from performing the calculus of variation. So first of all, the variation with respect to...
Sorry.
Is there a question?
Yeah, so that in particular, in the square root in particular, forces the phi, the scalar field, to have time-like gradient, yes?
Absolutely correct. Yeah, I didn't specify here, but we'll always have in mind the context where the scalar field has a time-like gradient. Absolutely. So this will in particular apply to a cosmological background.
Sorry, question.
Yes.
Can you comment at all? I mean, why are you looking at this particular form of sort of perturbation of standard Einstein situation? I mean, is there some insight where this thing comes from? Like
sure. It looks like semi-relativity. I mean, so the thing under the square root looks like 1 plus p squared. And when you expand with p is small, it looks like constant plus p squared over 2m. No?
Yes, that's correct. But let me. Okay, there's a few things I can say. First of all, the way I'm writing this right now, I haven't provided any motivation beyond saying, well, we have to look at something that differs from general relativity. And at this point, it just looks like, well, let's write something down.
Yes.
And let's see what comes out. And at this point, yeah, this appears really ad hoc. And maybe the polished way of formulating this would be to say that we would try to do bottom-up quantum gravity. We try to start with what we know and add things and hope that it builds into a consistent picture. And this is certainly a valid approach in physics. But there's also motivation coming from a top-down perspective where you start with a proposal for quantum gravity, which might as well also be ad hoc, because it's really hard to speculate what quantum gravity could be and see what the low energy regime of this looks like. And in both cases, there's motivation for this particular form of the action. I'm not discussing this right here, but yeah, I'm just saying in words that it's not really coming out of the blue. Okay, but for today, you just have to well, imagine it as being just speculated and see what are the implications.
So should we think of the phi here as being something like the amplitude in the Schrödinger equation?
Not really. Is there a reason why you're saying this?
Well, yeah, I mean, so the kinetic energy term certainly looks like that. And to some extent, the potential term does too, except that maybe it's nonlinear there. If V was quadratic in phi, then it would look like a linear Schrödinger equation.
Right. Okay, what I'll say is that here, at this point, I haven't specified what the potential is, and in the context we'll be interested in, it won't be quadratic. There are other contexts in which it could be quadratic, and in that case, yeah, I haven't really. I don't know if it's been discussed whether there's a connection with the Schrödinger equation in that case, but perhaps is Ghazal still there? Because maybe
yes, do you hear me?
Yes.
Okay, yeah. Do you mean that the equation of motion for phi is a Schrödinger equation? No, it does actually. All the time derivatives drop out.
Yeah, and I'll get to this. So
yeah.
Yeah. Right.
And in fact, that was why we came up with the square root.
Yeah, exactly. So that, yeah. So yeah, exactly. Let me move on, and we'll see why this particular theory is quite interesting.
Sorry, can I ask a question before we move on? How should I think of phi? Should I think of it as part of gravity or part of matter? Or another way to put it is, if you have additional matter species of field, how would phi couple to them or not?
Good question. So here at this point, I did not write anything else, but indeed you would have to add additional matter fields. And at this point, since this is an addition, we don't know whether it fits as matter or as gravity. The short answer is that it doesn't really matter. As you'll see here, I'll write it on the right-hand side as being matter, but you could also write this as being on the left-hand side, a correction to the Einstein tensor. And then when you add matter, then it's a choice. You have to decide whether this can, well, yeah, as a choice, you could say, well, maybe it couples, maybe it doesn't couple to the other matter fields, but then you have to check what are the implications. If it does couple, does it lead to any particular signals, any phenomenology, which would then allow you to constrain this field? Similarly, if it does not couple, again, is this sensible physically or not? So yeah, that's how you construct a theory to see if it makes sense. So at this point, it would not couple the way I'm writing it. You would just add matter fields and it would not couple to the matter. And usually this leads to sensible conclusions.
Okay, thank you.
Yeah. Okay, so yeah, the variation with respect to the metric gives rise to the Einstein field equations. And since, yeah, I did not write any matter content here, we just imagine being this as gravity and the Cuscuton field in vacuum. So we can view the Cuscuton as being the matter here. And in fact, it's going to have the same energy momentum tensor as a perfect fluid. And in that case, that's the form of the energy momentum tensor, where U is sort of the velocity field of this fluid. It's really the gradient of the scalar field divided by the square root of x. Rho is like the energy density, although in this case, it's the energy density corresponds to just the potential energy. So if you know scalar fields, this is somewhat unconventional. And then the pressure P is the combination of this potential energy and this non-standard kinetic energy. Then you also have to vary the action with respect to the scalar field, which gives you the field equation of motion. And in that case, the form of this equation is the following. So it's given by k equals to ml to the minus 2. So I didn't say, but ml is just some new mass scale, some new energy scale that enters when you write down this theory. This would be some fundamental scale of the theory, and the subscript L sort of invites one to think of it as a limiting curvature scale, as we'll see. And then this is multiplied by the derivative of the potential with respect to the field. And K here is really the divergence of the velocity field. And it really corresponds to the trace of the extrinsic curvature of a constant field hypersurface that has normal unit vector U. So K has the interpretation of a mean curvature here. There's a question? No, okay.
I have a quick question.
Yes, go ahead.
Is the square root important for getting a perfect fluid out, or would you have gotten a perfect fluid, maybe not with the same rho and P, but something else, even if you didn't have the square root on the of X?
Yeah. So generally for a scalar field that minimally couples to gravity, meaning that you don't have a coupling to the Ricci scalar here, you can always write this as a perfect fluid, regardless of the form of the kinetic term, whether it's a square root, whether it's x, whether it's x squared, you can always write this as a perfect fluid.
Really? Even like any function of x, like even e to the x or something? Oh, okay. Oh,
yeah.
I didn't know.
Yeah.
Thank
Could I
you.
ask? Could I ask? So how is this perfect fluid defined if phi is a constant field?
Right. It could not be a constant field because in that case it would not be time-like, and that is, yeah, I should have written down here. This is working under the assumption that the gradient is time-like. So you need sort of a time evolution. Yeah, because as we'll shortly see, we have in mind applying this to cosmology, and there it really it works well.
Okay, because you have a division by zero issue if you could have a constant. Okay, thanks.
Yeah, so we're avoiding this here because, yeah, x is always greater than 0. Okay, so about this last equation again, so the equation you get from the variation with respect to the scalar field, this one. So we would usually say that this is the equation of motion, but here it's really particular. So first of all, it indicates that having a constant field hypersurface here is really a constant mean curvature surface, because, well, the mean curvature will just be a function of the field. It's given by derivative of the potential, and the field on that hypersurface is constant. Therefore, yeah, the mean curvature is just constant there. Another thing we see from this is that if you have a potential that is nice, and by that I mean if its derivative is bounded, it's not nowhere divergent, then you're immediately bounding the mean curvature. And already we see that this might have the power of avoiding singularities in your space-time. Finally, what is important to notice is that this is not really an equation of motion in the sense that the scalar field is propagating, but really this is just a constraint equation. And what I guess the easiest way of seeing it is if we then apply to a particular metric. So again, having in mind cosmology, if we look at a flat Friedmann-Lemaitre, Robertson-Walker metric background, given by this expression where A of t is the scale factor telling us about the time evolution of the size of the universe. And this is assuming flat spatial sections, so this is just a Kronecker delta. Then this scalar field equation really reduces to the following, where the mean curvature is proportional to h, which Ghazal already introduced. This is the Hubble expansion or contraction rate. It's given by the time derivative of the scale factor, or the logarithmic time derivative, where a dot here is just, the derivative with respect to time. And yeah, here we see that this is just a constraint on the scalar field. It is not an evolution equation at all. In comparison, if you studied scalar fields before, you'll recognize the usual propagating scalar field equation of motion as being this one, where there it is explicit that there's a second time derivative on the scalar field phi, meaning that it will be an evolution equation for the field. And here there's no such thing. The field is really just constrained by that equation. And it's in that sense that the gravitational theory is modified, because and I'll get to this. Especially if we're in a cosmological background, it's quite explicit that we haven't introduced actually any new degrees of freedom. The scalar field is not propagating anything. So really we've only merely modified the theory of gravity, even though I wrote this field as sort of some new form of matter, but really it's not propagating anything. So it's only modifying the gravity. In fact, it's an example of what is known as a minimal modification of gravity. So this is a subject that is being studied in physics, in what ways we can modify general relativity by only having the usual 2 tensor degrees of freedom, the usual gravitational waves of gravity in vacuum, and nothing else, no other degrees of freedom, yet have something that differs from general relativity. In this context, as I said, since if we have a nice potential, we can bound the mean curvature. we can construct theories where we avoid singularities altogether. And for instance, we can construct non-singular spacetimes, non-singular cosmological spacetimes, such as bouncing ones, which would be solutions where we have first a contracting universe that then stops contracting at some finite size and then starts expanding after that. And the requirements to get this are pretty simple. You just need a potential which at the bounce point would have a negative potential, 0 first derivative and positive second derivative. So this sketch is just an example of a realization of such a potential. And then the general relativity limit would just be the regime where the potential is approaching 0 on either side. Let me show an actual example of this. So those are really solutions to the Cuscuton theory here. As a function of time, we have in blue, this is the scale factor. So it's going down, it's contracting. It stops contracting at this point. This is the bounce point, and it expands afterward. We can also view this as a function of the Hubble rate in orange, which is, as I said, proportional to the mean curvature in this case. When it's negative, this indicates contraction. Then it would go through 0 at the bounce point. And then when it's positive, it corresponds to expansion. And far away from this bounce, we're really approaching general relativity. And in between here, this is really where the Cuscuton becomes important. And that's where we have the violation of the null convergence condition. One way to view this is by looking at the time derivative of the Hubble rate, which is really proportional to the negative of Ricci contracted with a null vector twice. And so when this h dot is negative, we respect the null convergence condition, but when it's positive, then we're violating it. So here in this region delimited by the dotted lines, we have positive green curves. So we have positive h dot, meaning we're violating the null convergence condition, and everywhere else it is satisfied. Okay, now in the last few minutes, I'll discuss finally what was entitled stability. So I showed you an example of a background solution for this particular theory, but then we have to ask the question whether this speculated theory makes any sense. And from a theoretical perspective, we're going to ask whether this theory is stable and whether it is strongly coupled or not. And then we could also, well, we should try to find some observable predictions that would allow us to infer whether this really happened in the earlier universe or whether it didn't. So the main tool to address these questions is cosmological perturbation theory, which Ghazal discussed in her previous talk, where we expand the metric as some background quantity plus some linear fluctuations. For instance, we have scalar perturbations, and in a particular gauge, here this would be the matter comoving gauge. So this means that we set the matter fluctuations to 0, but just look at the metric fluctuations. We have alpha being the perturbation of the lapse function, so the function in front of the dt squared term. Then beta is a perturbation of the shift, the function in front of dt dx. And then zeta is like a perturbation of the curvature, the spatial curvature. And finally, we have also a perturbation of the Cuscuton itself. So we have some background profile and some linear fluctuations, delta phi. From the constraint equations of the theory, we can eliminate the lapse perturbation and the shift perturbation. And the Cuscuton also, since it respects a constraint equation, will have in the end not 0, but we're going to be able to eliminate this perturbation. In other words, it's not, as I said, it's not a propagating field in any way. Therefore, we can eliminate this delta phi from the equations. And what we're left with in the end is a single degree of freedom. The only one left is zeta, and this is known as the curvature perturbation. And then the action expanded to second order in this variable reduces to this particular form, which Ghazal also had in her slides, but maybe here it's written slightly differently. And what is important to see here is that there are a kinetic term and a gradient term. And if we want to address the question of stability, what this means is that we better have a positive function z squared here in front of the kinetic term, and this function cs squared in front of the gradient term better be positive as well. And I'll explain why in a minute. And this is the equation of motion that follows from this action. So in short, the kinetic term tells you about the propagation of this fluctuation zeta. And for it to be physically sensible, it better be positive. To show this, we need to dive into the quantum physics of it. And because I don't have much time, I'll actually skip a bit this slide. But what I'll say is that for scattering amplitudes, so compute probabilities of this fluctuation zeta to interact with itself, to respect unitarity, which is a notion of conservation of probability in quantum mechanics, you need to satisfy a certain theorem known as the optical theorem. And for this theorem to be respected, in general, you need a positive sign for this kinetic term, for this propagating term. Otherwise, if you have a wrong sign, you will have unitarity violation, and that's pretty bad usually, because then you don't have any notion of conservation of probability. I'm going to skip the notion of S matrix and this graph here to save a bit of time. I'll just say that at best, you can play some tricks so that you do not violate unitarity, but you will nevertheless run into a very severe instability of the vacuum, meaning that your vacuum would decay into eventually ghost fields. So that is the terminology usually used for fluctuations that have a negative propagating term. And these essentially propagate negative energy. So out of the vacuum you would have a runaway of negative energy. And if that were true, we wouldn't be here to talk. So this cannot happen physically. Then the other type of stability that we have to look at is known as gradient stability or gradient instability. To explain this one, we can look at the equation of motion and do some change of variable for the fluctuation, time and space. And this equation reduces to the following, which we recognize as the wave equation. That's why CS has this interpretation of a sound speed, so the speed of propagation of the zeta fluctuations. And that's how we can see that we better have a positive CS squared in order for this partial differential equation to be hyperbolic and to have a well-posed initial value problem. Another way to see this is if we Fourier transform this equation and look at the fluctuation in Fourier space, zeta sub k, and here I'm dropping all the tildes, but just to give you an idea of the solutions, with positive CS squared, the typical solutions for zeta are going to be sines and cosines. So either plus or minus I, k, the time integral of CS. So these fluctuations are really oscillating. But if we have negative CS squared, or if the sound speed is basically imaginary, then instead of sines and cosines, we have exponentials, plus or minus. So one of such solution is going to be a growing solution. And so the fluctuations are going to grow without bound. And so that's, again, a very severe instability. It's known as the gradient instability, and that's a sign that the theory is ill-behaved. So about the Cuscuton, I'm not going to show the calculations. That's maybe a bit boring. But let me just say that it's confirmed that the theory is linearly stable on a cosmological background, in particular bouncing ones that avoid the singularity. So there are no ghost and no gradient instability in that case. This is somewhat remarkable because it's actually hard to achieve if you have an effective theory that is geodesically complete. So if you have no singularities, it's been shown that in most cases, you actually run into either a ghost or a gradient instability. And the Cuscuton is able to evade this. Still, we have to address more questions to see if this is a reasonable theory, particularly whether the theory is strongly coupled or not. And that's also something that's usually very hard to achieve in a high curvature regime, such as a case where we have violation of the null convergence condition. But the Cuscuton is really behaving nicely. So perhaps it is not strongly coupled, and something that we are still currently investigating together with a PhD student in Waterloo. And similarly, we could then ask the question about whether there are specific observational signatures of a Cuscuton, and that is somewhat related. So this is something that we're also looking at right now, and both involve looking at the expansion of the action to third order in fluctuations. So very briefly, the idea is that if you go to the next order, for the perturbative expansion to make sense, you have to check that the third order is smaller than the second order. That's the very basic notion of perturbative expansion. And so you have to check all these terms respect this inequality. And also, you can then use these expanded actions to compute correlation functions. So compute the statistics of the fluctuations that can then be matched to what we observe, say, in the cosmic microwave background, such as the variance or the 3-point function. And yeah, as I said, this is to compute the 3-point function, which could have interesting signatures that we have to do these calculations, which we're doing right now. Finally, I'll just say that you could also think about doing this non-perturbatively, but in that case, you certainly need numerical techniques. You can't do this analytically, and particularly this would involve numerical relativity, but it's something also we're thinking about doing in the future. So take-home messages. General relativity has very nice theorems regarding singularities, but in quantum gravity, we don't know if they really apply. And in fact, the theory might well break down before we reach singularities. If we modify gravity in a high curvature regime, we might be able to avoid singularities, as I showed you. And then the question is whether such theories make any sense. Are they stable? What predictions they make? There are many open questions about the Cuscuton, whether it can be ultraviolet complete, meaning whether it can be extended to a theory all the way to high energy scales, as in quantum gravity. Then there's the questions about black holes. What happens to singularities at the center of black holes? Is the theory stable on any arbitrary background? We have to look at this. Also, a question that came to my mind: what does the existence of a constant mean curvature surface tell us? And perhaps these last few questions could benefit from mathematicians. And also, more generally, again, to connect the math and physics, are there tools that we can use to study and construct theories that have a notion of an upper bound on the curvature, or perhaps construct some theories that are actually non-smooth? What is the smooth limit in that case, the continuum limit? What are the tools of mathematics we can use to study physics on such backgrounds, and so on? So I hope we can discuss these questions in the thematic semester. That's it. Thank you.
Thank you, Jerome. Okay, so are there any questions? And for questions at the fields, I can't see, so someone will have to help me out there. I see DJ has his hand up. Yeah, DJ.
Thank you, Jerome. That was a very nice talk. So you mentioned black holes, and so I was wondering, if not a singularity, what is it that you would expect from the Cuscuton theory that would model black holes, say mergers, and then we also have this image of a black hole more recently.
Yeah. Okay. So about the Cuscuton, I don't know. But let me say that really it would only apply deep in the center of the black hole, if you will. And really the physics that's happening outside, so near the horizon and outside the horizon, wouldn't be affected. For the theory to make sense, it would, if it's changed, then it will be only small corrections. Then we can explore whether we can measure these corrections and if there are any signatures. But really, what these theories are trying to address is what happens in the even stronger curvature regime, really near the center of the black holes. And there, yeah, we really don't know what could happen. It could be that instead of a singularity, it could be wormholes. It could be there's some notions of bouncing black holes that are, instead of just collapsing and being there, they would eventually reappear, if you will. They would sort of evaporate and no longer be black holes eventually. I'm not an expert on those questions, but yeah, people are looking at this.
Okay, so just a small follow-up. So observationally, you wouldn't expect to see, apart from the bounce, you wouldn't be seeing anything else. And I guess that's also the motivation. You want it to be the same as classical relativity, right?
Yeah, well, general relativity is a very good theory. It's been tested and measured on various scales. And so there has to be some notion of recovering or having some general relativity limit. And in the context of cosmology that is discussed, we know that putting aside dark matter and dark energy, we know general relativity really applies well in the radiation-dominated era and the matter-dominated era. And so we have to recover the general relativity theory there. Before that, we just don't know. And that's where we can start exploring things that go beyond the Einstein equations and see if there are leftover signatures from that phase that we can measure and tell us about the high energy physics and yeah.
Thank you.
I have a question. So this theory depends on a, say, constant that is your maximum curvature. That is something you would consider a universal constant for, like, the speed of light, right?
Right.
So if you were just exploring the theory and you just took a sequence of predictions of what would happen, but now take the constant towards infinity, does this converge to general relativity with it just like a crunch and then a bang?
Yeah.
And that's been
The
explored?
short answer is yes. Yeah, correct.
Yeah. Thank you.
Yeah, I think DJ had his hand up first, so we'll do DJ and then we'll do Wilguy.
Thank you. I have more of a clarification kind of question. There was a slide where you talk about the failure of GR at the semi-classical level.
Mm-hmm.
So I'm not sure exactly I understood your reasoning. Maybe I can tell you what I understand as a semi-classical level understanding, and you can tell me if this is correct. If I start with a quantum theory of gravity, for example, defined by a path integral, by the way, I believe there's lots of connection to the math literature on non-smooth geometries because this object should be dominated by non-smooth geometries. That's on the side. So I start with this path integral and ask myself, what's the semi-classical description? Then it seems appropriate that I take the h bar going to 0 limit. And in this case, that'll single out the stationary points of the action as the dominating spacetime configurations to the path integral. So if I start with an action, say, which is the standard Einstein-Hilbert action, that tells me at the semi-classical level, I need to solve the classical equation of motion to obtain the dominating configuration. And in the quantum theory, there can be quantum boundary conditions. So the stationary points don't have to be real; they could be complex. They could describe tunneling processes, etc. So this is the story I have about a semi-classical approximation to a quantum theory, and it's not necessary that GR breaks down, because maybe these complex solutions, they avoid the singularity theorems and help resolve singularities. Could you comment on how this picture connects with your understanding?
Sure. Okay, what I'll say, what you said makes a lot of sense. And in fact, to compute transition amplitudes the way I discussed this right here, an alternative approach is to use a path integral formulation. And yeah, you can view this, the loop expansion I'm discussing here can be viewed also as an H-bar expansion. Here, I really neglected H-bar from the discussion altogether, but really, in the gravitational action enters the gravitational coupling constant Gn, and in the path integral enters H-bar. And in fact, if you compute the transition amplitude, you also have these H-bars appearing. So really, the expansion, I wasn't exactly correct in saying it's just G Newton, but it's some combination of G Newton and H-bar, which we usually combine together in what is known as a Planck mass. And it is this quantity that then determines the perturbative expansion, this coupling constant, the Planck mass. And there still exists a strong coupling regime. If you have energies that approach the Planck mass, you would still be in a situation where the 1/h-bar expansion breaks down, but it's not just H-bar, it's really M Planck. So the M Planck, you cannot, the M Planck to infinity limit would not apply, because you're at some high energies, and the higher you go in energies, the worse the theory becomes. So there's still a notion of strong coupling and a breakdown of general relativity as a semi-classical theory. So another way, last thing I'll say, another way of putting it, there's what we know as a strong coupling scale, or a cutoff to the theory, and for naively, this cutoff is given by the Planck scale, the Planck mass. Does that make sense?
Seems to me what you're saying. It seems to me what you said make total sense if I understand it as saying perturbative quantum gravity breaks down because you have a non-convergent series. Well, because of narrow normalizability.
Yeah.
However, I'm not sure that proves for me that the GR as a semi-classical equation that single out the stationary point for the action breaks down, because in any case, would you agree that when H bar goes to 0, the configuration that dominates the path integral is the one that is stationary for the action?
Yeah, I agree with this, and I think that's correct. All I'm saying is that it absolutely, as a low energy semi-classical theory, it makes perfect sense. But if you want to apply it at high energies, then you cannot, the theory won't be just stationary point. You would have to include the whole sum of loops, and which would contribute as much or even more than the saddle point. And so in that case, the 1/h-bar expansion just doesn't make sense. And that's what I'm trying to say.
I see. You're saying for the full quantum physics, one cannot rely on. Okay, I got it now. I see. Yeah, that makes sense. Okay, thank you.
Okay, Eric?
Yeah, so maybe my question's much like the last one. I'm not sure I can formulate it really very well, but So I guess I don't quite, I must have missed something. So at some point in time, I guess you're deciding that you don't want to have an initial or future singularity. So far, so good?
Yes, well, we're trying to see if there is a sensible theory that has no singularity, indeed.
Yeah. Right. But then the decision gets made that you will have something that's purely a classical field theory.
Right. So indeed. So So I discussed it as a purely classical theory, indeed.
Okay.
And so I looked at the classical background, classical perturbations on top of this. But then you could, in a similar spirit to what Ghazal discussed, you could then look at the quantization of the fluctuations on the classical background.
Sure. But
and you still have then to check whether that's where the strong coupling enters. You have to look at whether, from a quantum perspective, if this perturbative treatment makes any sense.
Right, but the thing you're quantizing is this matter field, this Cuscuton matter field.
Right, and then the fluctuation of the metric. So yeah, but they go hand in hand. Yeah.
So the hand in hand part I don't quite see. What
Okay.
if my metric is fluctuating, why does that tell me I have to have a Cuscuton field?
Okay, I don't know how to answer that part of the question, but the previous part, so I say that so the scalar part of the metric fluctuation and the scalar perturbation of the Cuscuton scalar field, they're both scalar fluctuations. And again, in the language of Ghazal's talk, the gauge invariant scalar degree of freedom in general will be a linear combination of these scalar fluctuations. So that's what I meant by saying they go hand in hand, and that is the quantity that we usually quantize. Now, you can work in a particular gauge where one of those is set to 0, and in fact, you're only discussing either the metric fluctuation or only the matter field fluctuation, and you're quantizing that. But in general, you're quantizing a combination of the scalar metric fluctuations and the scalar field fluctuation.
Yeah, I guess I'm really just asking why. I mean, if I wanted to avoid a singularity, I could presumably try to come up with some form of quantum gravity, or even just some form of weak extension of classical gravity without invoking. And if I were to invoke a field, I would probably open a book behind me and say, there's something called Brand-Sticky theory, and there's something called this, that. Mm-hmm. Why would I pick this one? Of all those options.
Well, I think that's how we do, in my personal opinion, I think that's how we do physics. The motivation for Brand-Sticky,
I would say though that if I were say sitting on a grant selection committee and somebody said, well, why not? I'd say, yeah, but okay, you're not getting funding. Go ahead.
Can I answer?
Sure. Yeah, please.
So
I'm interested.
So this is people have, so in the spirit of getting removing the Big Bang singularity, they have explored the other options, like Brand-Sticky. In particular, I don't remember that one, but like, for example, other modification of gravity. But the reason we choose this one is that this one is the minimal modification, as opposed to the other one. The other ones, they often lead to other problems that Jerome was alluding to, like instability, ghost instability, gravity. So this one is kind of.
Yeah, I would suppose. I mean, I don't want to dominate the question period, nor seem like I'm inimical to the idea. But along the way there was the division by 0 issue. Okay, well, so we assume that we're not dividing by 0. Yeah, but is that minimal to assume we're not dividing by? So, it doesn't strike. I wouldn't feel compelled to do it myself. Put it that way.
yeah, I mean, it's a little bit technical. Yeah, but so yeah, it is true that we are assuming we are perturbing around the FRW background. And the moment you do that, that denominator does not, it's kind of like goes hand to hand. You have, it should not be zero. It should have an evolving time direction, like, or it has to be like a space, like constant fixed surface. But yeah, it's yeah, we can discuss this maybe. It's
Sure, of course, yeah. Thanks.
If I might say something, it's very common for geometers to impose a lower curvature condition, which is similar to their higher curvature condition because they put absolute values on, and
even
we just
sometimes a
assume
higher
that the space has it, and we just proceed. And they're saying, well, we're going to say we're forcing it on the space and forcing it to have an evolution that makes it natural. So I would say that this isn't any different than all the Riemannian geometers saying, let's assume Ricci curvature is bounded below. Or
well, yeah, but of course, when Riemannian geometers do that, they're not usually trying to construct a physical model, unless perhaps they take it bounded below and then send it to zero. But I mean, I in some sense, I'm playing devil's advocate.
This is why I asked. What happens when you take that curvature condition to zero?
To zero,
to
yes.
infinity, to see if it was converting to the classic general relativity.
I'm just playing devil's advocate. I'm trying to. Thanks.
No, I mean, I just think that's why my question was, what happens if you take that curvature bound to infinity to see whether you're getting back to general relativity or not? Yeah. Or Einstein's equations or not.
I have a quick question. Just are there any, given Azal's talk previously, are there any connections to the power spectrum with what you guys are doing?
Yes. So,
you want to take it? Go ahead, Gisela.
So we do have a paper where we're trying to tackle that, and it looks like it's doable. Again, this is between us and observationalists. We get to the right now. We are at the point that we have the exact scale invariant power spectrum, but our goal is really we have to go beyond that. So those are all the laundry lists that we have to tackle one by one.
Okay. Okay. Great.
Maybe we could close the session and let people go that want to go and people want to stay and after the session.
I'm not hearing very well.
Oh, I was saying maybe we should sort of close the session and let the people go that want to go, and then if anyone wants to stay and ask further questions through either speaker privately and they're willing to entertain them, then we could do that.
Okay. Okay. Great.
Good.
Let's thank both Jerome and Azal again. So.
Thank you. I'd also just like to announce that next week, Robert McCann and Matthias Braun will be presenting a non-smooth approach to Einstein's theory of gravity, the time-like curvature dimension conditions on Lorentzian spaces via Reynolds entropy. So that's next week.
Cool.
Thank you, everybody. Take care.
Thank you.
Everyone, see you guys in a week.